So yeah, hi everyone. Today I'm very glad to host our own researcher from our lab, Alexandra. And yeah, as Danny just said, she will be presenting one of our recent works that will be published that will be presented pretty soon at AAC. Uh, and with that, I give the floor to Alexandra.
Right. So first of all, thanks everyone for coming. My name is Alexandra, and I'm a researcher at ML4C Lab at JetBrains Research. And today I want to talk about our work that is called From Commit Message Generation to History-Aware Commit Message Completion. And we did it together with my amazing co-workers, Yaroslav, Igor, another Yaroslav, Denny, and Timofey. And here is a rough overview of what I want to cover today. So I have a few introductory slides about the field, about the motivation. And next I have an overview of the approaches and datasets that researchers use for commit message generation. Then I have a few slides about the dataset of our own. Next, I will talk about experimental methodology, about our experimental results, and finally, I have a few conclusive slides about future work, about our resources, and so on. So that's roughly it. And at any moment, you can interrupt me and ask questions. I will not mind. I will be glad, as Danny said, it will be a good practice. So feel free. And I will try to keep an eye on the chat. But yeah, perhaps I might miss something. So if you have a possibility to ask with voice, it will be preferable. So let's dive right in and talk about commit messages. So what is a commit message and why do people care? Commit message is a natural language comment that you can leave when you commit changes in any version control system, for instance, Git. And since a lot of developers use version control systems in their projects, they face this necessity to write commit messages a lot. So it's relevant to a lot of developers all around the world. And good commit messages can be very helpful. They can help other developers in your project to understand what was going on at this exact point in history. They can also help yourself after some time if you get back to some old changes. So it's always a good artifact when you have good commit messages. But at the same time, a recent study has shown that poor commit messages might, in contrast, negatively affect the probability of introducing a bug in your project, negatively affect in the sense that it will increase. So commit messages are good, but like with any documentation, it's not always your top priority to write a great high quality commit message. If it will take your precious time, precious efforts, maybe you want to put them elsewhere. So that's why if you browse open source projects, you can find a lot of really simple, basic commit messages that don't tell you a lot about specific change, for instance, fixed bug or fixed typo. And several studies show, firstly, that many commit messages indeed lack important information and cover it only partially. And more older study shows that some of the messages in open source projects are even completely empty. So that's why there is an ongoing research on automatic approaches for commit message generation, which is formulated pretty intuitively. So we are given a commit diff, and we want to develop some model approach that will generate an appropriate commit message for this diff. And unfortunately, such research approaches are not as widely used in practice yet, but hopefully it can change. And our work is focusing on introducing a personalization aspect to commit message generation approaches. By the way, I have this CMG acronym here, and I will use it a lot. And it just stands for commit message generation because that's rather long. Why would we want to focus on personalization of commit messages? One reason for that is that the commit messages are very diverse. There is no single view on what makes a good commit message. Different people might disagree with each other. And one example are the conventions that exist and that a lot of people follow. And popular examples of such conventions are conventional commits, which really include a lot of interesting ideas. But one of them that you can instantly recognize is this prefix. Its purpose is to additionally specify the type of change. So here it's feed, so some feature is added, and also the component that is changed. So an API in this example, and it just gives some additional context to commit message, and it's also quite easy to write. And another very similar example is Gitmoji, which uses emojis for basically the same purposes, for classifying the different type of changes. So yeah, a lot of different conventions exist, and beside from general purpose conventions that can be followed by different developers in different repositories, there might also be some conventions that are specific to the project, or just some specific way that specific developer prefers to write commit messages. And while in usual commit message generation setting, we are simply given a diff, and there is no way for underlying approach to understand what is the current convention in the current repository. So it will just generate something the same, no matter what repository the diff comes from. And so we propose two ideas which might possibly help with the personalization aspect. And the first one is to focus on completion task instead of generation. And we have a figure here on the slide, and the difference between generation and completion is highlighted in the first column. Basically, in completion, we don't expect the approach to generate the full commit message, merely a continuation for a user type prefix, and we can vary the length of this continuation. For instance, if we have a very powerful model, we can generate a very long suggestion still just based on this prefix. Or if we have a less powerful model, we can use it to just suggest a few next tokens and still help. And the second idea is to use the previous commit messages that were written by the same user as additional context. And here the history is illustrated by the second column in the figure. So we just add both to generation and completion an additional input that is commit message history. And so why we want to do this? We have this very simple motivational example here. So we have a very small change. We just change something in the path. We remove the leading slash. And let's imagine that the ground truth message for this change was something like fix tree heat map data link. And it was also following conventional commits. And so let's imagine that the ordinary commit message generation approach, it generated remove slash and tree heatmap.rust, which is correct, but at the same time, it might fail to capture the underlying reason so that it's fixing something, and it also might fail to follow conventional commits convention just because it has no way to understand that it has to do it for the current change. And so completion, let's imagine that we are given some part of the prefix, and for the conventions like conventional commits or Gitmoji, a very important part of these conventions is actually the prefix. So if user gives us a large part of this prefix, the resulting output will follow this convention. And another great thing about using prefixes is that they might contain some additional information that might help to steer the model towards more relevant suggestions. For instance, here the prefix contains the word fix, so perhaps it would be easier for the model to understand that the underlying change, it's not actually just removing slash for whatever reason, but it's actually fixing something, fixing a path. So that's what we try to cover by the message that we generated for completion example here. And finally, commit message history. If the user has followed this convention throughout their previous commits, then if the model has an access to this database sort of commit messages that the user previously wrote, then it might follow the commit message conventions more closely. And it might, again, be wrong, as in our example here, but at least it will help it to use the correct convention. So that's it about our ideas. And next I have this little section about CMG approaches. So yeah, I guess I can just continue. They can be divided broadly into 3 different categories. And the first one is called language modeling based. And it's based on the fact that in commit message generation, we have an input sequence, so commit diff, and an output sequence, so commit message. So in a way, it is analogous to classic NLP tasks, such as neural machine translation or summarization or a lot of other tasks. And the researchers have tried to apply the same approaches that were successful in NLP to commit message generation. So specifically, they used language models, and language model is just some algorithm that is given a sequence of natural language tokens or code tokens, maybe, given a sequence of tokens, and it learns how to continue this sequence of tokens. Except in this case, since we have both input sequence and output sequence, the researchers have mostly used a more specific case of language models, that is encoder-decoder language model, which is called this way because it has 2 parts, an encoder which takes in input sequence and outputs some representation, and decoder that takes this representation and it should learn how to generate the output sequence. And about the specific architectures, so most recent CMG works used neural networks. The first work that proposed to apply language models to CMG used recurrent neural network. Then the later work also explored more sophisticated architectures like other RNN variants, transformer, graph neural networks, a lot of different language models that are also popular in NLP. And the next type of CMG approaches is retrieval-based approaches, and it's basically a way to apply k-nearest neighbors algorithm to this problem. And the way it works, it has sort of a preparation stage. So we have some train set for this task, and we go through each commit in this train set, and we use some algorithm to construct embeddings or vectors for commit diffs, and then we store them in a database. And in the first work related to CMG, simply bag-of-words approach was applied to construct diff embeddings. And after this preparation stage, we now have a vector database, and now we move on to sort of prediction stage or evaluation stage. And now we work on the test set, so on commits that we want to generate predictions for. And we go through all commits in this test set. Again, we construct a vector for their diff. And then we use simply cosine distance between vectors to retrieve the most close commits. And then this step is specific for CMG. Probably we go back from the vectors representation of this diff, of these diffs, to their text versions, and we compute a blue score for the diff of current commit with the diff of each retrieved commit, where blue score, I guess, is just something that allows to compute distance between strings at this point, and then we return commit message for the closest commit. And that's basically it for every retrieval-based CMG method. Later works tried more sophisticated approaches to construct vectors, so not only bag-of-words, but maybe, again, neural networks, and something else that, again, comes from NLP mostly, or they try to tweak other details, but the overall algorithms have stayed the same. And the final group is hybrids, which just combines ideas from both retrieval and language modeling, and it comes in 2 flavors. The first one is when the generation module, so language model and retrieval module, they are sort of independent, so they coexist. And then there's also a third module, a ranking module, that receives the output from language model, the output from retrieval module, and it chooses the best one among them. And the second approach is to actually use retrieval inside of language model. So change the architecture of language model somehow, so it would take not only the current diff, but also the diff from retrieved commit and the message from retrieved commit, and it will improve her predictions somehow. And the model following this approach was actually state of the art in commit message generation, at least at the moment of our experiments. I'm pretty sure that it's also state of the art now, but just to be safe, at least it certainly was at the moment of our experiments. And the last thing I'd like to say about the CMG approaches, of course, they are not perfect. And one of their problems is that they can pretty often generate completely irrelevant prediction. So there is example on the slide with a simple diff and examples from 3 different CMG methods. And they all generated something that has nothing to do with the actual code, the actual change. And of course, it's very bad for any practical usage. And so what researchers have been trying to do to overcome this, the first thing, of course, is to develop better CMG approaches, which won't generate relevant predictions and which will just, well, improve over the old ones. And another thing that was tried by several researchers, it's actually based on the human evaluation scores that were received in one of the words. So in the figure on the slide below, you can see that 2 most frequent scores for the quality of the generated commit messages are either 0 or 7. So either they are very bad or very good. And so the idea is to develop some automatic algorithm that takes in commit message generation by the model, also maybe diff, and it outputs if this message is appropriate to use or not. So sort of quality assurance filter for underlying models. And we believe that the completion idea that we propose might also help in this case, because completion is sort of simpler than generation, and it can lead to, well, some practical usage of existing models, even if they are not powerful enough for generating the messages from scratch. And that's it for CMG approaches. And I'm moving on to CMG datasets. So there is a great study from 2021 that did an overview of all existing datasets and introduced a dataset of their own. And here I have a table from their study which lists the datasets, lists which programming languages these datasets contain, how many commits are there, and what is the content about each commit that these datasets provide. And you can quickly notice that a lot of these datasets share the same limitations. So early works mostly focused on the Java programming languages. The datasets were also quite small, so they only contain on tens of thousands examples. And another limitation is that they only store diffs and messages and not many metadata about each commits. So there was no way to trace to GitHub, for instance, to gather some additional information or anything like that. And so this work introduced a great dataset MCMD, which doesn't have these limitations. But going back to the ideas that we propose, we had some additional criteria for the dataset in mind. Firstly, since we want to explore personalization that is sort of tied to different commit message conventions existing in the wild, the first thing we wanted from the dataset is to be diverse. So it should contain a lot of different commit messages, not only just one convention, but a lot of them. And another thing, since we wanted to experiment with commit message history, we wanted the datasets to be suitable for that. So to provide the metadata like authors or timestamps, or at least, again, hashes and repos, so that we could gather them ourselves. And also we wanted the datasets to preserve commit history to a reasonable extent, which will probably be more clear a bit later, because I will show the counterexamples to that. So a part of our work was exploring existing datasets to find a suitable dataset. And since we had this section about our own dataset, you can probably guess that we didn't find them. So let's dive into the problems that we found in existing datasets, again, according just to the ideas that we wanted to experiment with. The first one is that a lot of datasets actually introduce very restrictive filters in the stage of data processing, so that actually contrasts with our diversity requirement. A lot of filters here are pretty self-explanatory, and I will comment on them a bit on the next slide. But what I'd like to highlight here, there are a few pretty interesting filters that researchers introduced on the commit message structure. So it's probably the less desirable for us, again, in terms of diversity. And the first filter that was used is called verb direct object, because it restricts the data sets to commit messages that start with verb followed by direct object clause. So here I have a simple example, refactor code. So refactor is a verb, and code, it's, well, the simplest case of the direct object clause. And an example of commit message that doesn't follow this is minor refactoring. And other options include limiting the commit messages to only those that start with curated set of verbs. So for instance, only fix, add, remove, and so on. And so we have this table here, which lists all of the CMG datasets and the statistics on whether they use each filter or not. And if there are some relevant details, these details as well. And we found that actually a lot of filters are repeated throughout different works. For instance, the most frequent ones were first sentence, which means only considering the first sentence from commit message, which is often used as some sort of summary. So perhaps you've seen this on GitHub, where it highlights the first sentence in bold, and you have to click additionally to extend to next sentences. Another frequent filter is limiting the commit messages to those with less than 30 or 20 even tokens. And there are also, again, message structure filter, which I briefly commented on. And another frequent filter is filtering by the length of commit diffs. And if you look at the exact number of tokens that researchers frequently restricted on, a lot of researchers have resorted to 100 tokens, which is pretty small. So the existing datasets mostly contain quite small messages and quite small diffs. And you can also notice that there is a first dataset by Loyola et al., which doesn't use any of these filters, but it was created earlier than MCMD, so it actually falls under one of the limitations mentioned there. I think it uses only the commits from several selected repositories, so like tens at most, which is not very representative for our case. And the second criteria that I was talking about, so the commit history one way of leaving only a small fraction of original commits is to filter them with a very strict filter. So for instance, in one CMG work, the data set was filtered to only keep commit messages with less than 30 tokens, diffs with less than 100 tokens, and it led to a reduction of 96%. So of course, if you look at commit history in the resulting data set, it will only contain a fraction of the original commit history. And another processing step that sort of messes up the commit history is to perform train validation tests split randomly. It was also something undesirable for a dataset. And finally, some of the researchers decided to randomly downsample from the original set of commits, so only choose a small fraction of the original set of commits intentionally, for instance, to ensure that the distribution among programming languages is the same how it was done in MCMD dataset. And so we arrived to a necessity to build our own dataset for experiments. And I'd like to briefly cover the steps that we followed. The first thing we did is we selected the appropriate projects and we used the GitHub search tool, which is pretty cool and convenient for various MSR purposes. And we used several criteria from previous work just to ensure that the datasets are, well, good and relevant. And another thing I'd like to highlight here is that we only selected datasets with permissive licenses. And so when we did this selection on January 25th in 2023, we selected almost 12,000 suitable repositories. And so we collected commits from them using another pretty cool and convenient tool called PyDriller. And here we set several filters for commits now. So we excluded merge commits, we excluded commits made in 2016 and earlier, just to, well, focus on the most recent and relevant ones. And we also had this technical limitation of excluding commits with more than 10,000 changed lines. Just because such commits are quite rare, and also because they require a lot of resources to process. And so when we collected the data on February 9th in 2023, it was almost 30 million commits. And now we have a pretty rigorous data processing, which I'm going to cover briefly because otherwise it will take too long. So what I'd like to note, a common motivation here throughout the steps is that we didn't want to introduce a lot of restrictions in terms of commit message structure or anything similar, but we still wanted to ensure data quality and do some basic processing like deduplication, or for instance, drop some automatically generated examples, because there are a lot of them in open source projects on GitHub. So we have some steps in processing related to identifying and dropping commits from pod's account. So the first thing we did is we split the data by projects in order well, not to break the history, for instance, by splitting randomly. And by splitting the data, I mean on train validation test splits. And also another comment here about the splitting is that it was shown in previous study that it's more complicated than the random one, because in the random one, well, the model usually sees the commits from the project it's later tested on, and it can gain some understanding, some context about this project. The next step that we did is we dropped outliers, and here outliers I meant in sense of several length-related features, so the number of words in diffs, in messages, the number of characters, the number of changed files. So it's again probably more of the technical limitations, because such examples are quite rare by the way we designed this filtering step, and they are also hard to process because they are very long. So we computed the percentiles for these features, and we dropped all the examples larger than 95th percentile. And this is a quite heavy processing step. So we dropped almost 20% of the commits on the previous stage. And as for processing commit messages, I probably won't go into much details here, but again, the idea was to drop the examples that are automatically generated. So for instance, again, we filtered the messages that Git uses for revert commits, for merge commits. If for some reason they weren't filtered by PyDriller, these squashed commits and so on, just something that is out of focus of our study or not doesn't represent what human developers write. As for processing commit diffs, we dropped examples with empty diffs that might appear, for instance, due to renaming files, copying files, or something like that. Then we had the duplication step, which is again quite heavy, and it resulted in almost 25% of commits on the previous step being dropped. And finally, we had this processing commit offer step, which is pretty vague because it actually includes 3 different steps. And well, probably one of the interesting ones here is that we used existing bots datasets to find bot accounts and to drop commits from them. And another thing that we did is named disambiguation. So if we use the pair of names and emails to represent a commit author, then in fact, it might turn out that the same human in the real world has several such entities. For instance, the simplest example is when you have a work email configured on your work machine and you have a personal email configured on your personal machine, but you share the same username. And if you look at these emails, perhaps you might even notice that they are quite similar. So there is a special tool, again, for solving such matches, but it works by computing various string distances for all pairs of authors. So it was pretty much infeasible for us to run it on the whole data set. It would take forever. So instead we used it in per repository fashion. So for each repository, we ran disambiguation on all the authors that commit there. And in a sense, it's pretty logical because the same person is likely to commit to not so many repositories, but at the same time, it's sort of a limitation. And finally, as a result of all our processing, we have around 10.7 million commits left out of almost 30 million, so around 1/3. And well, we have 20 programming languages in our data sets, and we have retained 11.9 thousand repositories. And on the right of the slide, there is also a table with more detailed statistics in per programming language fashion. And so what we also did for a data set, we computed the statistics for the most frequent filters, such as diff length, less than or equal to 100 tokens. And we found that some of these filters are indeed very restrictive. So for instance, if you only consider diffs with 100 tokens or less, we would filter out 84% of commits. And similarly, if we used verb direct object filter for message structure, we would only keep around 36% of commits, so less than half. Sorry, can you hear me now?
Yes.
Yes.
Again.
Cool. Sorry, I just had a strange sound from my headphones. I thought maybe something went wrong. And also we checked how our processing affected commit histories, because we did drop almost 2/3 of the data set. So for each author, we computed the number of commits before all processing in our data set and the number of commits after the processing in our data sets. And we found out that we retain 67% of original commit histories on average. And the last few comments about our dataset is that we included not only diffs and messages, but also metadata, so authors and timestamps, which are required for working with history, and also general metadata like hashes, repos, I think something else as well, perhaps languages and licenses, something like that. And also we published our dataset, so you can download it and use for future research. And moving on to the methodology of our experiments. So let me remind you that we introduced two ideas. The first one is to focus on completion setting instead of generation. And the second one is to try using commit message history as additional input. And we have two research questions which address exactly that. So A1 and B1. And we also have two additional research questions. A2 is targeted at LLMs in comparison with CMG approaches from research works, just because no one has tried to apply LLM to commit message generation before in research papers. And the fourth research question, B2, it's about the influence of data filtering steps, since data filtering takes quite an important place in our work. And we considered three different models from research works, which are COT5, which is just a general purpose model for tasks around software engineering, which was applied to a lot of them, including commit message generation. The second model is RACE, which was proposed specifically to CMG, and it's a hybrid model, so it shares both retrieval and language modeling ideas. And the final model is Code Reviewer, and it's a bit different from the first two in the sense that it wasn't previously applied to commit message generation. It was applied to code review data, but code review data means diffs and review comments, which is in a sense quite close to commit messages and diffs. And this model specifically in its pre-training objective had a task where it learns to produce efficient diffs representation. So we thought that it might be relevant for CMG as well. And as for LLMs, we only tried a single one, which is GPT 3.5 Turbo, and it's a model from OpenAI, which is closed source, so it's only available through their API. And a few words about our input setting for the model. And the first point is what we did to simulate sort of completion. So in the real world, it can be actually a separate task to determine when you should invoke completion model. So what should be the prefix that you pass to the model and when it should start generating. And in our experiments, we decided to go for this setting. So we selected some sort of parameter x, and we decided to take first x% of characters of each commit message as prefix and treat the remaining characters as targets. And we explored three values for this x parameter, which we sometimes refer to as context ratio. So 0, not passing any prefixes at all, just usual generation. Then 25 and 50, so just two different ratios of length to compare how the quality evolves if we pass the larger portion of commit messages to models. And below there is a simple example. So consider we want to compute prefixes for 25% context ratio, and we have a very simple message fixed typo which has 8 characters. Then if we compute the length of the prefix, it will be their product, and well, also rounded to take an integer, and it will be 2. So the first 2 characters of fixed typo will be a prefix, and the remaining would be a target in our experiment. And now moving on to the part specific to CMG approaches. All of the approaches we considered are encoder-decoder language models. And so let's start with completion. Firstly, the training procedure for completion and generation tasks are absolutely the same, and the difference appear only during evaluation. And so they are highlighted in differences between the first and the second row. So in generation, we want to generate the full message, and we don't get any additional input related to the message. And in completion, we get a user type prefix as input, and we want to generate a continuation. And as for the history, what we did for commit message generation models, we decided to take as much history as fits into the decoder's context, and we concatenate all the messages from history, again, as until they fit to model's context. And we also concatenate it with current prefix or current commit message. And when we use history, we use it both during training and evaluation, but we mask it in loss so that the loss won't be computed on the history, only on actual predictions. And as for LLMs, basically, since we only consider a closed source LLM and it's available through paid API, it can be considered just like some black box which you throw a text into, and it gives you a continuation for this text. And in our setting, we went for the simplest option possible everywhere. On the slide, you can see almost the exact prompts that we used for language model, almost, because GPT 3.5 Turbo is actually a chat model and it requires a slightly different input format, but our system's messages were really simple as well, but they wouldn't fit to the slide. So we only provided a simple example without any additional instructions or context. So write a commit message for a given diff or complete a given message for a given diff. And for history here, we went for a different setting from CMG models. So for CMG models, we concatenate as much messages from history as fit to their context. And here we only take a single previous message. So it's, again, the simplest possible option and a baseline of what can achieved via LLMs in CMG. And another point of methodology is hyperparameters, and I'm probably not going to go into much details here. So probably the most important thing is that we used 512 as the context length. And we also trimmed diffs to first 512 tokens for GPT 3.5 Turbo to match our settings for CMG models. And also we allowed models to generate up to 15 tokens during evaluation. And as for the training, basically we took all the important hyperparameters from previous CMG study, which experimented with similar models. And as for the data we used for our experiments, we used the dataset we introduced in the study, except it's full test, it's huge. It's around 1.5 million commits. And so instead we went for two different subsets. The first one we used for experiments with CMG models, and it takes around 200,000 commits. And the second we used for experiments with LLM, since, again, the one we chosen is available through paid API. And we went for a much smaller subset, so only 4,000 commits. And finally, the last but not least, the metrics that we use for a study. The first one is bnorm, which is probably not familiar to any of you, but it means just specific implementation of blue metric, which should hopefully be familiar to more people. And this implementation is shown in previous CMG study to be the closest to much human labels. And blue metric, it's a classic metric in NLP that was introduced for neural machine translation and then later used for many other tasks. And basically it's based on word overlap between the predictions and the references. And that's probably it about blue. The next two metrics are probably more relevant for completion setting. So the second one is edit similarity. It's a metric based on classic edit distance between string, and it has a nice practical intuition that was highlighted in one of the previous completion studies. So users might be willing to accept a suggestion even if it's wrong. If it's not too hard to edit it to the right one. So edit similarity is basically just normalized edit distance, which measures exactly how hard it is to edit one string to another. So it has this nice intuition to it. And exact match, it's basically just a percentage of perfect predictions in generated sequences. So the number of generated sequences that exactly match the reference ones. And another comment about metrics, we not only computed them as usual between generated and reference sequences, we also took the prefixes of these sequences of different lengths, and we computed the metrics for these prefixes. And the intuition here is that such setting allows to check how the quality evolves as we generate more and more tokens. And it's again in line with this idea of completion being useful both for long generations for more powerful models and for shorter generations for less powerful models. And now let's proceed to our results, except I have a quick comment here. We consider a lot of different configurations in our study, and of course we didn't have enough space in the paper to include results for all of them, and I won't talk about all of them as well in this presentation, but we published all of them and they are available on our website as something human readable and in our repository as JSON lines files. And let's proceed to the results. So the first research question is related to completion. And we present results in this paper. And these gray rectangles are here simply because what they cover is not relevant to this research question. And I hope it will make it a bit easier to understand. So the first finding is that we noticed that indeed the quality grows as we pass the larger prefixes to models context. So there are differences between both pure generation setting and the first completion setting, so 25% context ratio for all the models and all the metrics, especially for exact match metrics, but that's not surprising, considering that the way we structure the input for our models, frequently the first word that the model has to complete in completion setting is the suffix to some word, and it's easier to choose the right suffix than choose the right word from all the words. And well, there is also a growth between 25% context ratio and 50% context ratio, so it's easier to complete half of the message than, well, 3/4 of the message. Yeah, I guess that's it. That's how it's called. And another finding related to these research questions is that we compared these three CMG approaches between each other, and we were surprised to see that they are very close in terms of almost all the metrics. The difference is less than 1 point in absolute values. And we also performed statistical tests here. So we used Bootstrap, and in almost all the cases, the races prevalence over the remaining two models was statistically significant, but still the absolute difference is very small. And now here you can see also plots which represent the metrics between prefixes. The x-axis here is the number of tokens in prefixes, and the y-axis is the value of corresponding metric. And ignore the dashed lines for now. They correspond to models of history, which we will talk about a bit later. And we noticed two interesting patterns here. So firstly, for completion, performance consistently drops as we ask the model to generate more and more tokens, which is pretty intuitive, and it aligns with the findings that were reported in previous study on completion that used the same idea with metrics between prefixes. But we noticed an interesting pattern for generation. So if you look at edit similarity plot, it starts to decrease consistently, almost consistently as well after 4 tokens, but before 4 tokens, it actually grows. And yeah, the generation plots are on the left of the slide, sorry. And when we explored the examples where edit similarity for 2 tokens was less than added similarity for 4 tokens manually. We found out that in a lot of cases, it's due to these prefixes being present either in target data or in models output. So a lot of commit message convention, for some reason, they go for adding certain prefixes to the beginning of commit messages, like conventional commits or something else also. And probably in generation setting, it's hard to generate the correct prefix. And it was also quite surprising that sometimes generation models do try to generate prefixes so they can randomly follow the conventional commits, for instance, for some examples, because it's a very popular convention. But yeah, it's not clear why they do this for some examples and not for others. And now moving on to the second research question that is related to LLMs. So here is where we start showing not full results. In previous table, there were results for all 3 context ratios. And here we only report results for the completion setting for 25% context ratio. And again, the gray rectangles just mask the history, which is not relevant at this moment. So what we found out is basically that GPT 3.5 Turbo performs worse than fine-tuned CMG approaches, all of them, again. But note that our setting is the simplest possible, and it can likely be greatly improved by some more advanced pro engineering. And we also noticed an interesting pattern when looking at metrics between prefixes. Here again, they are presented for 25% context ratio. So for shorter sequences, GPT 3.5 Turbo is again worse than Code T5, but as the number of tokens in prefixes grows, it actually becomes better than Code T5, so it can hold great potential for generating long and detailed messages. I didn't highlight it on the dataset slide, but actually we also tried to compute the statistics for the filter message length is less than or equal to 30 tokens. And we found out that almost 90% of our datasets of commit messages in our dataset, they are indeed 30 tokens or shorter. So commit messages in open source projects tend to be quite short. So the models trained on them, it can be hard for them to generate long and detailed sequences. And so perhaps GPT 3.5 Turbo or other LLMs might be a good choice for CMG in such setting. And moving on to history-related research questions. So what happens if we add commit message history to CMG models? Here is the full table for metrics for CMG approaches. And if you look at all the metrics in generation setting and compare them between the models used with history and without history, then the models trained with history are consistently better. But if we look at completion settings, so for instance, 25 context ratio, then the bnorm and edit similarity improve, but the exact match metrics don't. So the results are a bit more conflicting than for generation, and similarly for 50% context ratio too. And another interesting thing to note is that if we look at plots between metrics, so on the left are plots for generation, and there again we can see that the models with history outperform the models without history. So these dashed lines, they correspond to models with history. And if you look at completion plots on the right for 25% context ratio, then the models with history are almost the same, or they even start to underperform at some point. So the history and completion together certainly require further research. And we also checked what happens with GPT 3.5 Turbo. Does it benefit from adding this previous message to its context? And we found out that yes, it does. So both in terms of metrics between full predictions and references in the table, and in terms of metrics between prefixes for all the prefix lengths. adding history did improve GPT 3.5 turbo results. And the final research question is about how do the common data filtering steps affect results, what changes with and without them. And here I have a quick comment about our setting for these research questions. So we chose 3 frequent filters from CMG research, only using first sentence of commit message, limiting the commit messages to those that follow word direct object structure, and also limiting the commit messages to those that have 100 tokens or less in diffs. And so we found out that in our test set, there are 10,000 examples that fit all the filter and around 22,000 examples that fit none of the filters. And we selected subsets of the equal size. So all the examples that fit all the filter, a random subset of the same size, and a subset of the same size of examples that fit none of the filters, which we call out of filters. And here are the results for the models on these 3 different subsets. And again, they are only presented in 25% context ratio, and the findings are exactly roughly the same for other context ratios too. And the first thing we found out, if you look at random subset and on filtered subset and check how the history affects the metrics, then, well, they improve, except for the random subset and exact match. But if we look at out of filter subset, there all the metrics actually become worse when we add history, and it certainly also requires further investigation, because intuitively the history might have been helpful for these commits that don't fall under some more restrictive setting with filters, but actually it doesn't. And another observation from this result is that if we compare the results on filtered subset, for instance, for race model, which is the best one in all the metrics, with results on random subset, then the results on filtered subset are significantly higher. So perhaps if we use these filters to process the data set, the results may not always be representative. They might not transfer to commit messages and, well, commits in general outside of those filters. And in contrast, if we compare the results for examples that don't fit any of the filters with just randomly chosen examples, then the results are drastically worse. So for instance, Code Reviewer has binorm 6.37 on out of filter subsets, while it has a binorm 18.4 for random subset, which is 3 times decrease. So there are certainly commits that current CMG approaches not really deal with well, and they require future research. And that's it about our work. And I'd like to just quickly talk about some possible future directions that we may explore or other researchers may explore. And firstly, while we introduced these 2 ideas related to completion and history, we merely did some initial exploration for them, which is especially concerning commit message history. We only considered a single setting for integrating a history to CMG approaches. Perhaps they don't need all the messages. Perhaps they need like 1 message or 5 messages, and it would be interesting to investigate how it affects the results. And another possible idea for future research here is that adding commit messages to models context might not be such a great idea at all, because it leads to the increase of context size and worse performance in terms of time complexity. So perhaps it might make sense to develop a separate model that would be able to construct developers' writing styles or project conventions based on commit history, and then use the representations from this model in CMG models. another group of future research directions is related to large language models. So again, we investigated a really simple setting in our study, basically a baseline, and only a single LLM, GPT 3.5 Turbo. First of all, it's closed source, and perhaps it would be interesting to check how the open source models can handle this. Secondly, it's not the most advanced model. Even OpenAI has GPT-4, and perhaps it would be interesting to compare their results. And again, better results can be obtained if we use more sophisticated prompts. Another interesting idea is that all the metrics we used in our study are based on either words overlap, so binorm, or characters overlap, like edit similarity, and it might not fully capture the semantic aspects behind quality. So if a human developer looked at the output of our models and decided whether they useful or not, perhaps their judgment might not correspond to these metrics perfectly. So human evaluation might uncover new insights for all our research questions, I believe. And alternatively, since human evaluation is very hard to collect and very expensive, perhaps it would be interesting to explore how recent semantic metrics work for CMG. Do they correlate well with human judgment or not? So for instance, something like BERT score and its variations, or maybe using LLMs like GPT 3.5 Turbo or GPT-4 for evaluating more precise semantic aspects. And finally, since we introduced this diverse dataset here, the question of data quality is surely even more important for this dataset. So all these restrictive filters that researchers applied, they were there for a reason. They tried to, well, increase the probability that their data is good this way. And perhaps, and even though we followed some, I guess, basic processing steps, and we dropped a lot of automatic examples, we performed the duplication, still, I believe our dataset can be further improved by filtering, especially in terms of commit messages. And also, our results suggest that there are commits that current CMG approaches especially struggle with. So this out-of-filter subset from the last research question, it might be interesting to research why they struggle with them and how we can overcome it. And that's it. I will just leave our results here. So here is the QR code for our website, which should hopefully work. It worked for me. And we have a published code for our experiments. We have a preprint for a paper. We also have published our data set and all the models from this work. So thank you very much for attention, and I will be glad to discuss any questions.
Thank you. Thank you, Alexandra. So any questions, please raise a hand, write in the chat, ask with your voice, whatever is find suitable.
Sorry, just a moment. Apparently my headphones died during my presentation, so I will just switch to another headphones. Sorry. Right, I'm back, hopefully.
Yes, we can hear you.
Yeah, I can hear you too. Great.
Let's see who wants to be the first one to break the ice and ask some questions as if you were seeing this presentation at the ASE conference.
Hey, Alexander, I have a question.
Sure.
My name is Alex. I work in machine learning team. And so for the incorporating history into the language model, how exactly did you do that? As part of the input, I presume, somehow?
Yeah, we just concatenated it with, well, the actual message during training. Oh, let me get back to the slide. It's not very detailed here, but what we did, we just concatenated the history with the current message.
Mm-hmm. Did you try various order of things there? Because, I mean, it seems to be that those models are quite sensitive to the order of things.
Yeah, we only tried a simple setting here, both in
Okay.
terms of order and in terms of, for instance, the number of messages in history. And I believe it might indeed make sense to experiment with that. So perhaps it's not the most optimal setting.
Got it. And a couple of questions about the data. So did you quantify how common are the conventions, like, conventional commits or emoji ones, or?
Yeah, that's an interesting question. I think I computed statistics for conventional commits at some point, but I don't remember it, nor do I have it anywhere. I guess it might make sense, but again, there are a lot of different conventions, and perhaps you should come with some predefined conventions to compute these statistics.
Mm-hmm. Yeah, I'm just curious. I'm seeing that in different data sets or in various places, but it would be interesting to have an idea if it's like, 5% or 35%. Yeah. And for the mining part, did you use all for the repository that you mined? Did you use all the reference in those repositories, like all the branches, like websites and the code and, whatever pull requests there, or did you filter those?
Yeah, I believe we used only commits from main branches, so
Okay,
not all the branches.
got it. And you mentioned the deduplication step. Could you explain a bit what is the duplicate in this sense? What exactly were,
Yeah, sure. I actually have a couple of more detailed slides about the dataset. Maybe I've mentioned it there. Not really, I didn't, but I can answer still. So we computed duplicates either in terms of diffs or in terms of messages. So if at least one of those two features were the same for the examples, we grouped them together and we only left a single example of all such groups of duplicates. And we performed the deduplication by exact hashes. So we computed the hashes of these strings and dropped the examples with the same hash.
Mm-hmm. Makes sense. Yeah, thank you. And then sorry, go ahead.
Sorry, just follow up for dropping string hash duplicates, but wouldn't it remove commits of the fixed back or fixed type kind? Or do I miss something?
Well, yeah, but that's kind of desirable, I guess, because they are mostly trivial and less interesting than other examples. At some point, we also wanted to perform, well, near deduplication, but the approach I tried, it was pretty hard to run it for this scale. We used some, I think, older tool, Sorcerer, CC, something like that.
So would it be fair to say that in the commit message completion or generation, we want to have no commit messages like fixed type or fixed back?
Yeah, I believe the less we have, the better. So there was a study, I think, from ICSI 2023, which actually observed that a lot of messages in open datasets, they tend to follow very simple patterns, so like update some file, add something to something, and so on. And so they computed the ratio of such patterns both in the datasets and in model outputs, and they found out that, well, if you reduce the number of such examples in the dataset, then the model trained on this dataset will also produce less such simple example. And likely you want the model to produce something less trivial than, I don't know, update readme, because you could just write it by a simple rule.
All right. Okay. Thank you. Sorry for barging in, Alex.
No. Good questions. And I think it's very important to understand that diverse, and then the dataset serves a specific purpose, that it would not like a lot of changes that hide behind fix commit would be lost and they're not there. If you care about things like that, maybe you should look for other datasets, and that's really good to know. And for dataset, a couple more questions. So with private identifiable information like emails, did you keep those, or did you replace, author name by hashes or something like that?
Yeah, so for author identifier specifically, we use this name disambiguation tool, which basically produces an integer for each author after merging their identities. So we just use these integers in the final data set. As for the personal information in the data, we actually didn't filter the diffs at all. We did have a couple of such examples filtered out in commit messages, but in the end data set, I also decided to provide the original messages too, because for instance, we remove references to issues and pull requests, and perhaps they might be useful for some researchers. So for such personal information, I guess we don't remove it.
What I meant is that in Git, you would have this metadata as the author and it would be part of the diff, but here I guess it was not, right?
Yeah, it was not. So we basically used the output of PyDriller tool, and it returns almost the whole diff, but I believe without this initial Git header, which is diff -git, something like that.
Yeah, got it. Yeah, I'm not familiar with the PyDriller. Yeah, makes sense. Yeah, and for the author, this match, like author identification and kind of matching, why do you think that was needed for this study or for this data set? I mean, wouldn't just kind of, leaving it as is be good enough, or what's the advantage?
Yeah, so you mean this name disambiguation step at all? Yeah, perhaps it just makes sense for our study specifically since we focused on history. So if, for instance, someone has several different configurations of name and email in the repository, but it's still the same developer, I guess they are likely to have the same conventions or writing styles still. Maybe there was some Git misconfiguration or something like that. I frequently run into this myself.
But what I mean, did you take advantage of this like bits of knowledge while building the histories, or do you think someone might do it later and that's why it's there?
Yeah, I guess we didn't measure any advantage, and I can think of the way of measuring it on a spot, I guess, in this case, because we would just have different inputs and different targets, so just a bit different benchmark in a sense.
Okay. And I didn't have a chance to look deeply into the paper yet, but I wondered, did you quantify the diversity of the data set? I mean, in terms of like lengths and some statistics like that?
Yeah, so we don't provide information like that in the paper because, again, there is not much place. But I have this pretty long Jupyter notebook with various statistics about the dataset in the repo.
Okay.
Yeah, I can, I guess, add it here or something like that, or to our website or to dataset page. Yeah.
No, this repo is good. I mean, perfect. And like I have two more questions. If anyone wants to ask other things first, I can wait.
Yeah, Alex asked those, and then I have some questions myself. So yeah, go on, ask your questions.
Okay, so metrics part, you mentioned the exact match, and I wonder, is it case sensitive?
Yeah, it was case sensitive. It was like the exact match.
Okay, and then exact match at 2. What is that at 2?
Oh, sorry, I forgot to comment on this. I actually wanted to do this, but I forgot. So, for exact match, we actually only report the scores for prefixes of either 1 or 2 tokens because it very quickly deteriorates to 0, and there are not many perfect predictions even for like 3, 4 tokens or more, or for full sequences too. So basically, exact match at X means that we only consider the prefix up to X tokens, X first tokens.
And first tokens after the percentage used for completion, right?
Yeah, so first tokens in remaining part as well for completion.
Got it. Oh, yeah, that's really nice. And you mentioned that there are studies showing that particular flavor of blue metric is correlated with human evaluation. And you also mentioned that future work could be kind of more specific study how much quality of life of developers improved. What's like the impact of those things? Maybe if you have few words to say about that, because that sounds really interesting. I mean, in practice, you would have a strong argument if you could show something like that, to build up a system using a model like it.
Yeah, so that study is pretty cool, but actually what it does, it just compares the 3, I believe, or well, let's just say several different variations of blue among each other and shows which one is the best in terms of correlation with human judgment, which is also great, but at the same time, it doesn't mean that this is just a great metric overall. It just means that it was the best over those that existed. And I think there is, of course, limitations to what extent might this overlapping based metric catch some more interesting semantic aspects. Perhaps for our approaches specifically, it might be interesting to check if they follow the same conventions or something like that. Or for instance, there is this frequent problem for CMG approaches, at least the research ones, not for LLMs, that they generate something irrelevant completely to the content of diffs. And perhaps it would be great to compute metrics like that. So if this commit message is even relevant or not. So perhaps, if some semantic metrics can be researched, I think it would be pretty cool if they could also be more targeted, sort of, so not just evaluate quality in general, perhaps, but some more finer grained quality aspects.
I see. Yeah, this sounds really interesting, and then we could use another model to grade that if we have those, dimensions. Interesting. Yeah, thank you very much for the presentation, and I'm done with the question.
Yeah, thank you for the questions.
Yeah, thanks, Alexander. It was a very, very nice presentation. So very informative, you introduced very well a lot of the concepts that we used, and very, very thorough. So the only problem that we have at ASC is that we don't have so much time. But I would love for people if someone at ASC will say, well, I want to learn more about this. I say, well, I have a longer version of the presentation, and I don't know if you can share the recording from today or the slides from today.
Yeah, I guess they usually post it on YouTube and it's public.
Yeah. So my first question, and again, I'm asking again, I'm putting myself in the shoes of someone in the audience. So going back to this, exactly where we are at this slide with the semantic similarity, and so here we are measuring with both the B norm and the edit similarity and exact match. We're measuring exact match. So in cases where the numbers were not like the difference was large, did you manually analyze to see at least if the commits were very different, it had like zero overlap, but it was exactly the same thing, it was semantically equivalent? I'm just wondering if you analyze some of these, and then maybe a hope for a semantic similarity tool maybe the numbers will look very differently. I understand we cannot manually analyze millions of such commits, but I'm just wondering if we analyze some and then you said that they were semantically equivalent or they were completely very different. They didn't talk about the same things.
Yeah, so that's an interesting question. I guess I certainly didn't do it to any large extent. I think the setting where I explored and compared the predictions the most is the LLM one, which is coincidentally opened right now. So I compared the predictions from GPT 3.5 and CMG models, and I can't recall a lot of specific examples where GPT 3.5 was great, but it was for some reason rated really low by those automatic metrics, so B-norm, edit similarity, and others. But what I noticed is that it generally tries to follow rather different message structure compared to those CMG approaches. So again, it usually tends to generate something more detailed, more verbose, but maybe still making sense, but rated lower because the original message wasn't as detailed. It was closer to the shorter commit messages, maybe not fixed typo kind, but still pretty short.
So that was my second question about, because that's a very surprising result that LLMs perform worse, but as you were explaining it, they perform worse because the quality of the original commit message it's not great. Like people are don't want to say lazy, but people are slacking in writing a quality message. Say it was almost like 25% of the commit messages were of this, fixed type or fixed a bug or something. So that's completely useless, right? And then the remaining maybe were more useful, but still of lower quality. And you are saying that an LLM will do a good job at summarizing a diff and will produce something could be more verbose, but maybe it's of higher quality than a very terse message that the Oracle had with the commit message, right? That's what you're saying.
Yeah, so for LLMs, perhaps that's why history helps more consistently than for CMG approaches, since we didn't provide any additional example of what should be the structure of this commit message, and it just chooses it on its own. Perhaps the history can just help it to show what is expected. So don't generate this huge paragraph here, generate just the summary and stuff, and that's why it helps more. But that's just the hypothesis. And also, again, we checked a really simple setting for LLMs, and I believe it can certainly be improved significantly. And you also have to be careful with these more detailed predictions, because it gets harder to even evaluate them and to understand again if they make sense. It takes way less time for shorter commit messages. Perhaps you can instantly see when it's just noisy, and if you have to read this paragraph, and perhaps the model also tries to infer some reasoning which is not actually there. It just gets more high level, complicated sort of.
So in the case of it was a one-shot learning, we sent only one single example for the LLM. So here is a sample of the kind of commit message structure that someone had for a previous diff, right? So it was. So I'm wondering if we fill up more to the maximum, like the buffer, I don't know how many characters are 1,024 or 2,000 or what's the number of characters that you can fill up the buffer. If we fill up all of that with giving several such examples, not just one, but giving as many as we can to fully maximize the buffer, whether you play with that, whether that will improve the quality or will make the LLM generated message be more succinct, more terse, more. I don't know if you've experimented with that, with fully maximizing the buffer that it's allowed for an LLM prompt.
Yeah, so we didn't experiment with that, and actually we not even tried one-shot learning. We tried like half-shot, I don't know how to call it, but we didn't provide a previous diff. So the model didn't have an example of how to solve this task. It only had a message to like help it understand the conventions and stuff. But I believe that both providing examples perhaps and providing messages only, more messages than one, could certainly be beneficial. I think it would be interesting to experiment both with CMG approaches in the same sense and with LLMs, and to check like how many messages you have to provide. Does it stop improving the results at some point, or does it improve consistently when you add more? Because if we suppose that the history helps by providing conventions, some way to see and understand these conventions, then perhaps it doesn't require all of the messages, well, as much as fit into the context. For LLMs like GPT 3.5 Turbo or GPT-4, it can be a huge number actually, since they have this huge context.
So the beauty of this first study that you've done, it's that it's massive. The scale is massive, like nobody else has done something at this scale, right? And when you work at this scale with millions of commits, you cannot do a qualitative comparison. So I'm wondering if you have some plans to do instead of doing a quantitative comparison with exact overlaps and stuff like that, if you can do something qualitative, or say it's a much more smaller set, and maybe we can involve the original authors of that particular commit, and we say, hey, here is what you originally submitted with your commit. This is the message, and what do you think about, give us a rating about here is another alternative, or here's a couple of alternatives for your commit, right? And see whether people prefer those alternatives that were generated by LLMs, or so this is more of a qualitative study that doesn't measure the exact overlap, but it asks people, and it's better to ask the original developers because they are the most informed, right? They are the authors, they are the most qualified to tell us what they think about the proposed an alternate commit message for whatever they first wrote. Do you have some plans to further expand this with a qualitative analysis comparison?
Yeah, so I think it's a great idea. It's, well, I believe it's pretty close to this more semantic evaluation, more advanced sort of than these automatic metrics can cover. And I believe it's very interesting. We don't have such plans at the moment, but perhaps we might do something to this area sometime.
Yeah, perhaps this will be a good project for an intern, if we can have an intern in the near future.
Yeah, perhaps.
Good. Yeah. Who else has other questions?
Thank you so much, Danny, for the questions and for the comment about my presentation.
Yeah, pleasure.
Yeah, so just in case we're about out of time, so I guess there is some time for one or two quick questions, and I propose the rest of the crowd who wants to carry on, we just can stay in the Zoom meeting, but we'll stop the recording soon. So one or two quick questions, folks.
Hi. Thank you for your presentation. I have one brief question or like clarification. You said that you use in commit message completion task, you use a prefix and it like fix characters there, and then you complete. Why it's not fixed tokens? Why you like count characters, not tokens, and afterwards you say that you can calculate metrics by tokens, and I do not understand like a link between these two things.
Yeah, thank you for the question. I think it's pretty mixed in our results, in a sense that sometimes, like when talking about hyperparameters, I refer to tokens like BPE tokens, So subword tokenization that is used for all the underlying models. And when talking about results, I mean tokens like the actual words, so not split somewhere in the middle, but rather split by spaces or something like that. So yeah, sorry about that. Perhaps I should work on the wording. And as for the questions about the characters here instead of tokens, I guess it was to also encounter this real world situation, like in this example here, for instance. So it's not always invoked on complete tokens. Completion tools are not always completing when you've typed a full token. Sometimes they're called also in the middle of a word. And well, if you use the characters instead of tokens, we can also add such situations and see how they're handled. We also have this, well, additional approach of correctly generating the continuation for prefixes. Probably I won't go into much details because I'm afraid I might not make it well, but we have it described in our paper. I think it's called token healing or something like that.
Because I think it's not fair, like if you fix 8 tokens and in one situation is a half of the word and in another is like full words a bit before it, it's not fair to like compare, but it's okay. Maybe you face such an example where it's like better or worse when it's full tokens in this prefix or not.
Yeah, that's probably like might be not fair to compare like one setting 25% context ratio with 50 in that sense. But since we do this for the whole data set, I guess it should be kind of evenly distributed. So the number of examples which are trimmed for parts of words and the number of examples which are trimmed to full words. So yeah, and I don't think we explored such examples manually, but this trick that I just talked about, so token healing ones, we experimented with and without it, and it brings a pretty noticeable gain in completion setting. And also, I personally think that the huge difference in exact match between generation and completion, it comes purely from these prefixes being beginnings of words, and well, that the models should just output suffixes and not the whole words.
Okay, thank you for answering.
Thank you for the questions.
So once again, thank you, Alexandra, for presentation, and we'll stop the recording now.